13 billion years ago, a black hole 50 million times heavier than our Sun is already feeding, and its galaxy barely exists yet. The child is older than its home. James Webb just caught it. We will fly to a red dot smaller than a whisper of the Milky Way, to gas purer than anything alive today, and to a monster that may have been born in the first second of time. If this stuns you, like and subscribe. Hold on, we begin. Somewhere in the deep sky, a single red speck has been hiding a secret for 13 billion years. Astronomers pointed the most powerful telescope ever built at it, expecting a small, quiet galaxy. They found a giant instead. At the centre of that speck sits a black hole, and that black hole appears to be older than the galaxy around it. Say that slowly. The thing that should have grown last grew first. For most of history, we believed the order was simple. A galaxy forms, stars are born, live and die. When the biggest stars collapse, they leave black holes behind. Over billions of years, those black holes eat and merge and swell into the monsters that sit at the hearts of galaxies today. The galaxy is the parent, the black hole is the child. This red speck breaks that story in half. Its real name is a jumble of letters and numbers, so we will just call it the red dot. It shone when the universe was young and raw, only a few 100 million years past its birth. Back then, galaxies were tiny, dim and still gathering their first stars. Yet inside this little smudge, a black hole was already enormous. Monstrously oversized for its age and its home, far beyond anything the rules allowed. Picture walking into a nursery and finding a newborn who already weighs as much as a grown adult. You would freeze. You would question everything you thought you knew about how babies grow. That is the exact feeling that swept through the science teams when the measurements came back. Something in the young universe had built a giant far too soon, and for a while nobody could say how. The telescope that caught it is the James Webb Space Telescope, a golden eye the size of a tennis court, floating 1 million miles from Earth. Engineers built it to see the faintest, oldest light in existence, the glow of the first objects ever to shine. When it stared into one crowded patch of sky, this red dot stared back, brighter and stranger than anyone predicted. The first question was simple. What is it? A galaxy full of stars? A single feeding black hole? Something with no name yet? The light alone refused to confess. It arrived smeared, reddened, and tiny, carrying clues that took teams on 2 continents months to unlock. What they slowly realized was worse, and far more thrilling, than a normal galaxy. The light was pouring out of matter, screaming as it fell into a black hole, far more of it than any crowd of stars could ever explain. And when they finally weighed that black hole, the number made no sense inside the old rules, because if this black hole is as heavy as it looks, then it came first, before the galaxy that should have built it. It may have been born massive, in a way our textbooks never allowed. That single idea, a black hole older than its galaxy, pulls a thread that unravels the entire story of how the universe grew up. Pull that thread, and you reach the first stars, the first light, and maybe the first instant of time itself. But to see this creature at all, Webb had to do something that sounds like pure magic. It had to look backward through time. Every time you look at the sky, you're looking into the past. The sun you see is the sun as it was 8 minutes ago, because that is how long its light takes to reach your eyes. The nearest bright star you can spot at night is showing you years of history. Push that idea to its limit, and a telescope becomes a time machine made of glass and mirrors. Light is fast, yet the universe is almost unimaginably wide. When light leaves a distant object, it sets off on a journey that can last billions of years before anything on Earth catches it. So the farther away something sits, the older the picture we receive. We never see the deep universe as it is now. We see it as it was. The red dot is one of the farthest things we have ever measured. Its light has been racing toward us for more than 13 billion years. When that light first left, our sun did not exist. Earth did not exist. There were no planets, no oceans, no life anywhere that we know of. There was only a young cosmos, freshly lit, still figuring out how to build galaxies. The image Webb captured shows that object as it looked just 700 million years after the Big Bang. Compare that to the age of the universe today, close to 14 billion years. Squeeze all of cosmic history into a single year, and this snapshot was taken in the first few weeks of January. We are peering at the newborn universe while it is still in its crib. This is why the Golden Telescope had to be so extreme. The light from such a distance arrives faint, stretched and drained of energy. As the universe expands, it pulls the light waves longer, shifting them out of the colours our eyes can see and into infrared, the range we feel as heat. A normal telescope would find nothing there. Webb was designed to drink in exactly that stretched, ancient glow. Think of it like listening for a whisper shouted from across an ocean, a whisper that has been slowly lowering in pitch the entire way. You would need an instrument tuned perfectly to that fading sound. Webb is that instrument, chilled colder than the deep space so its own warmth cannot drown out the signal it hunts. And here is the part that bends the mind. Because the picture is so old, everything we say about this black hole is a report from the ancient past. Whatever became of it since, we cannot know yet. The monster we are about to study may have grown into something even more terrifying in the 13 billion years its news took to reach us. We're reading a very old letter, and the sender has long since moved on. So Webb gave us the letter. It showed a red dot glowing at the dawn of everything, holding a black hole that should not be that big that early. Yet catching the light was only the beginning of the trick. Because this object is so faint and so far, even the greatest telescope ever flown could barely make it out. To pull it into focus, astronomers needed help from something enormous sitting between us and the dot. Something so heavy it bends space itself. A trap of gravity that turned one faint smudge into three. In the image, the same object appears 3 separate times. That should be impossible. One object, one place in the sky. Yet here was a single red dot printed 3 times across the same picture, like a ghost caught in 3 mirrors at once. The explanation is one of the strangest tricks in all of physics, and it turned a nearly invisible speck into something scientists could actually study. Between us and the red dot sits a colossal cluster of galaxies. Astronomers gave it a fitting nickname, Pandora's Cluster. It holds the combined weight of trillions of suns, all packed into one region of space. Anything that heavy does something remarkable. It bends the space around it, the way a bowling ball bends a stretched trampoline. Light has to follow that curved space, so when the faint glow of the distant dot passes near the cluster on its way to us, its path bends. Sometimes the cluster splits that light into several routes, and each route delivers its own image of the same source. One faraway object arrives at our telescope as 2, 3, or more copies. The cluster works as a giant, clumsy lens. Albert Einstein predicted this over a century ago. He realized that gravity is not really a force pulling on things, but a warping of space and time itself. Mass tells space how to curve, and curved space tells light how to travel. For decades, the idea felt abstract. Now Webb uses it as a tool, letting nature build a lens far bigger than any humans could ever construct. Picture looking at a candle through the bottom of a wine glass. The flame smears, brightens, and splits into repeated shapes. The glass simply bends the light already there, gathering it up and stretching it into new shapes. Pandora's cluster does the same to the red dot, except the glass is made of galaxies and the candle is a black hole at the edge of time. This lensing did 2 priceless things. First, it magnified the dot, making it brighter and easier to catch than it should ever have been. Second, it produced those 3 copies, 3 chances to measure the same object, 3 angles on the same ghost. If a result showed up in all 3, scientists could trust it was real and not some fluke of the camera. Without that lucky alignment, the red dot might have stayed a meaningless smudge, too dim to weigh, too small to trust. The cluster acted like a cosmic gift, a magnifying glass placed by chance exactly where astronomers needed one. They did not build it. They simply found it and looked through it. And what they saw through that natural lens only deepened the mystery. Even magnified 3 times over, even pulled close by all that bending gravity, the object stubbornly refused to look like a galaxy. It stayed a dot, a tiny blood-red point of light that would not spread out into the swirl of stars everyone expected. That refusal became its own puzzle. A whole galaxy should look like something. It should have shape, structure, a glowing disk or a fuzzy ball. This thing had none of that. It sat there as a single crimson pinprick, and its stubborn smallness would soon tell astronomers something they were not ready to believe. When Webb first swept across the early universe, it kept finding strange red freckles scattered through the dark. They were small, they were red, and they made no sense. Astronomers started calling them little red dots, a plain name for a deeply confusing discovery. Our red dot is one of the clearest examples ever found, which is why teams chose it for the deepest study. To understand the monster inside, we first have to understand why the dot itself is such a riddle. Start with the colour. In the early universe, young objects tend to blaze in bright, energetic light because they are full of hot new stars. A deep red glow suggests something older, or dustier, or hidden. Finding rich red colour this early is like finding grey hair on a toddler. It hints that something about the usual story is wrong. Then there is the size. When the telescope tried to spread the dot into a shape, it failed. A normal galaxy, even a small one, has width. Zoom in and you see it stretch across the sky, a smear of countless stars. This object stayed a point. Whatever powers it is crammed into a space so tiny that the sharpest telescope ever flown still sees only a pinprick. That combination broke people's brains. To shine as brightly as it does while staying that compact, an ordinary galaxy would need to pack its stars unbelievably close together, far tighter than any galaxy we have ever seen. Squeeze that many suns into that little room and the object would look nothing like the calm, spread-out galaxies around us today. So astronomers faced a fork with two paths. On one path, the dot is a galaxy stuffed with an impossible crush of stars. On the other, most of that light is not starlight at all. It comes from a black hole, feeding so hungrily that the gas around it glows brighter than a galaxy full of suns. Picture a single street lamp against a whole city skyline. From far away, both can look like the same small glow. The question is whether you're seeing a million tiny windows or one blazing bulb. For the red dots, that question decides everything about how the early universe worked. For a while, nobody could tell. The light carried both possibilities inside it, tangled together. A dot this small and this bright could be a dense knot of stars, or it could be a black hole wearing a thin cloak of gas. The two answers point to completely different universes, and the stakes are enormous because Webb has now found these red dots by the hundreds. They form a whole hidden population, blooming across the young cosmos and then fading away, far too many of them to be rare accidents. Whatever they turn out to be, there are enough of them to rewrite a chapter of the universe's history. Our particular dot became the test case, the one clear enough and magnified enough to finally settle the argument. To crack it, scientists needed more than a picture. A picture shows brightness and colour, and that had already led them to a wall. They needed to weigh it. They needed to reach across 13 billion years and put this thing on a scale, and the first number they wanted was the one that seemed the simplest of all. How big, in plain miles, is this impossible little dot? The first shock was the sheer size of the whole thing, long before anyone reached the black hole. Our galaxy, the Milky Way, stretches about 100,000 light-years across. That means light itself, the fastest thing there is, needs 100,000 years just to cross from one edge to the other. It is a spinning city of hundreds of billions of stars, so vast that our sun takes over 200 million years to make a single lap around its centre. Now shrink your imagination. Shrink it hard. The entire red dot, the whole glowing object with its monstrous black hole and its cloud of gas, measures only about 1,300 light-years from side to side. Set that beside the Milky Way and it nearly vanishes. You could line up more than 70 of these objects across the width of our galaxy and still have room to spare. It is a speck compared to the spiral we call home. To feel that gap, imagine the Milky Way as a sprawling country the size of the United States, stretching coast to coast. On that scale, the red dot would be a single small town. And crammed into that tiny town is a black hole heavier than the black holes lurking in galaxies thousands of times its size. The whole neighbourhood is smaller than a whisper, yet it carries the weight of a scream. This is what stunned the astronomers. Bigness and heaviness usually go together in space. Giant black holes live inside giant galaxies, surrounded by oceans of stars, Here the container is tiny and the thing inside it is huge. The proportions are all wrong, like finding a blue whale living comfortably inside a backyard pond. The small size also explains why the object looked like a mere dot no matter how hard Webb squinted. There simply is not much there to spread out. Most galaxies are wide because their stars are scattered across enormous distances. This object keeps almost everything packed into its cramped centre, which is exactly what you would expect if a black hole and not a broad swarm of stars dominates the whole show. And that tiny size carries a warning about the gas inside. In a normal galaxy, generations of stars spread out and enrich a wide region over billions of years. A place this small and this young never had time or room for that slow, sprawling history. Whatever fills it should be simple, raw, and close to the original recipe of the cosmos. So the picture sharpening in the scientists' minds was this: a tiny bright town, far too small to hold the crush of stars its brightness would require, glowing mostly from the fury of a feeding black hole at its heart. Every clue pointed the same direction. Yet clues are not proof. Brightness can fool you. Colour can fool you. Even size can be argued about. To truly nail it, the team needed the black hole's weight, measured directly, with no guessing. For years, that had been the one thing nobody could do for an object this ancient and this far. Every earlier measurement of these distant giants leaned on assumptions borrowed from black holes nearby. This time, the team found a way to weigh the invisible, and the method they used is one of the oldest tricks in astronomy. The same law that keeps the planets on their leashes around the sun. You cannot see a black hole. By definition, it gives off no light of its own. So how do you weigh something you cannot see, across 13 billion years of space? You watch what it grabs. A black hole is silent, yet its gravity is loud. Anything nearby feels its pull and starts to move. Gas swirls around it, stars swing past it, whole clouds get yanked into orbit. Measure how fast that material races around, and you can work backward to the mass tugging on it. The faster things whip around a centre, the heavier that centre must be. We already trust this logic every day without thinking. The planets in our solar system obey it perfectly. Mercury, close to the Sun, sprints around in just 88 days. Distant Neptune crawls along its far orbit, taking well over a century for one loop. From those speeds alone, using nothing but the law of gravity, you can calculate the mass of the Sun without ever touching it. Speed and distance reveal weight. The team pointed Webb's most delicate instrument at the red dot, a device that splits incoming light into its full rainbow of colours. Hidden inside that spread of colours is motion. When gas moves toward us, its light shifts slightly bluer. When it moves away, the light shifts redder. By reading those tiny shifts across the object, scientists mapped the swirling gas like tracking wind on a weather chart. What they found was clean and beautiful. The gas near the centre moved fast. The gas farther out moved slower, in an orderly, graceful fall-off. That exact pattern is a fingerprint. It is the same pattern the planets trace around the Sun, where the inner worlds race and the outer worlds dawdle. Astronomers call it orderly orbital motion, and it only appears when almost all the mass sits concentrated in one tiny point at the centre. That single detail cracked the case wide open. If the object were a fat swarm of stars spread across its whole width, the gas would tumble in a messy, complicated dance, tugged in many directions at once. Instead, everything circled one dominant heart. The gravity came from a single point, and a single point holding that much mass, giving off no light, can only be one thing: a black hole. Picture a whirlpool in a river. Watch how the water spins, faster near the drain and slower at the rim, and you can sense the size of the hole pulling it all down, even if the drain itself stays hidden underwater. The astronomers read the whirlpool of gas and measured the drain they could never see. With that clean, planet-like motion in hand, the math was simple and honest. No borrowed guesses, no assumptions dragged in from nearby galaxies. Just speed, distance, and the same law that has governed orbit since the days of the first astronomers. For the first time ever, someone weighed a black hole this deep in the young universe directly. The result landed like a thunderclap. The black hole tipped the scale at roughly 50 million times the mass of our Sun. On its own, that is a genuine giant. Yet the truly frightening part was the comparison that came next. Raw size was only the beginning. Because when the team measured how much everything else in that little dot weighed, and stacked it against the black hole, the ratio broke every rule they had. Here is the number that keeps astronomers up at night. The black hole, all 50 million suns of it, makes up at least 2/3 of the entire mass of the object. Every wisp of gas, every faint star, every scrap of matter in that whole glowing dot added together weighs less than the single black hole at its centre. The monster is not a resident of this place. The monster practically is this place. Sit with that. In everything else we have ever studied, the black hole is a tiny guest inside a vast home, a dark seed buried deep in a fruit the size of a mountain. Here the seed has swollen until it is heavier than the entire fruit around it. The proportions have flipped completely upside down. To see how bizarre that is, we need a comparison from home, and we will meet that comparison in a moment. For now, hold on to the raw strangeness. 2 out of every 3 units of weight in this object belong to a thing that gives off no light and swallows everything that falls in. The visible glow, the gas, the hints of stars, all of it is the minority. The darkness is the majority. This is what forced the scientists to say out loud the sentence that sounds absurd. The black hole appears to be older than its galaxy. Because if the galaxy had formed first, slowly building itself from stars over hundreds of millions of years, then the stars should dominate and the black hole should be a small fraction hiding inside. The opposite is true here, so the natural reading is that the black hole came first and the galaxy is only now, barely beginning to gather around it. Imagine a town where a single skyscraper weighs more than every house, every road, every person, and every tree combined. You would not assume the town grew up first and later added the tower. You would suspect the tower was always the centre, and the town is only starting to sprout at its base. That is the red dot, a tower with a town just beginning to grow around its feet. The measurement came with unusual confidence, because of that clean orbital motion from the last chapter, and those 3 lensed copies checking each other. This was a direct weighing, honest, and repeatable, which means the flipped ratio is real, and the flipped ratio has consequences that ripple through everything we thought we knew. If black holes can be this dominant this early, then somewhere in the first few 100 million years of the universe, nature found a way to make an enormous black hole quickly, before galaxies had time to build themselves the normal way. Our whole tidy story of galaxies raising black holes like children starts to crack. One young astronomer on the team put it bluntly. Most of the mass, he said, sits in the black hole at the centre, and if it was spread among many stars instead, the gas would never move in that clean, orderly way. The motion itself proves the darkness dominates. So we have a black hole that outweighs its own home 2-to-1 in the infant universe, breaking the natural order of things. To understand just how insane that ratio is, we have to turn around and look at our own galaxy, at the sleeping giant hiding in the centre of the Milky Way. Our own galaxy has a monster at its heart, and by the standards of the red dot, our monster is practically polite. Deep in the centre of the Milky Way, hidden behind thick curtains of dust and stars, sits a supermassive black hole. Astronomers call it Sagittarius A star. It weighs about 4 million times the mass of our Sun. For years, scientists tracked stars whipping around an invisible point near the galactic centre, watching them swing on tight, fast orbits around nothing visible. Those orbits gave the game away. Something dark and heavy was steering them, and in the year 2022, telescopes captured the first true image of the glowing ring of gas around it. 4 million suns sounds terrifying, and it is. Yet here is the humbling part. Compared to the whole Milky Way, our black hole is a speck of dust in a cathedral. Add up all the stars in our galaxy, the hundreds of billions of them, and the central black hole accounts for only a tiny sliver of the total, roughly 1 part in 1,000. The galaxy is the ocean. The black hole is a single drop. That ratio holds across almost every large galaxy we have ever studied nearby. Big galaxy, comparatively small central black hole. The black hole matters, it shapes its surroundings, it lights up when it feeds, yet it stays a minority partner. The stars own the galaxy. The black hole rents a room at the very centre. Now set our galaxy beside the red dot and feel the whiplash. In the Milky Way, the black hole is 1 drop in an ocean. In the red dot, the black hole is the ocean, and the few stars are the drop. The difference between those two ratios runs into the thousands, a gulf so wide it stuns the mind. The early object breaks the pattern by a factor so large that scientists first assumed they had made a mistake. Picture two families. In the first, a normal household, the smallest child is a baby, dwarfed by parents and older siblings. In the second household, the baby weighs more than the entire rest of the family put together. You would demand to know what strange thing happened at that second child's birth, and you would not rest until you understood it. The red dot is that second family, and the whole field of astronomy is now demanding an explanation. Our sleeping giant took billions of years to reach 4 million suns, growing slowly along with the galaxy that cradled it. It followed the rules. It grew up gently, in step with its home, the way the textbooks describe. It is the well-behaved version of the story. The red dot followed no such rules. It reached 50 million suns in a fraction of the time our galaxy needed to reach a fraction of that. It did not grow up gently alongside a galaxy. It seems to have arrived already massive, then waited for a galaxy to catch up. So the contrast sharpens the mystery to a knife's edge. Same kind of object, a supermassive black hole, yet two wildly different life stories. One grew slow and stayed small relative to its home. The other grew impossibly fast, or was simply born huge and dwarfed its home from the start. The next clue came from the gas itself, because when scientists read the ingredients of that gas, they found something almost frozen in time, a substance that has vanished from the universe we live in now. When the team read the chemistry of the red dot, they found a recipe almost as old as the universe itself. Everything in space is made of ingredients, and those ingredients leave signatures in light. Split objects glow into its rainbow, and dark and bright lines appear at specific colours, each one the fingerprint of a particular element. Hydrogen writes its name in one place, oxygen in another, iron in another. Astronomers read those fingerprints the way a detective reads a smudge of ink. The red dot's fingerprint was startlingly plain. Almost the entire object is hydrogen and helium, the two lightest and simplest elements in existence. The heavier stuff, the oxygen and carbon and iron that make up planets and rocks and living bodies, is nearly absent. This gas is stripped down to the barest ingredients, close to the raw material the cosmos started with. To grasp why that matters, we have to go back to the beginning. When the universe was born, it cooked up only the lightest elements: hydrogen, a great deal of helium, and a faint trace of a couple of others. That was the entire menu. Everything heavier came later, forged inside stars. There was no oxygen to breathe, no carbon for life, no iron for cause. Only the plainest gas spread thin across the young dark. So finding gas that is almost pure hydrogen and helium is like finding untouched wilderness. It tells you almost nothing has happened here yet. No generations of stars have lived, burned, and died to enrich the mixture. The red dot is holding on to the original recipe of creation, barely altered, at a moment when most places were only beginning to change. Scientists measure this purity with a single number, the amount of heavy elements compared to what our sun contains. The red dot came in at less than 1/200th of the sun's level. That makes it one of the most pristine places anyone has ever measured, anywhere, at any time. It is a fossil of the early universe, preserved in light that took 13 billion years to reach us. Picture a glass of water so clean it holds nothing but water, no minerals, no dust, no trace of anything living. Now imagine that in the entire modern world such perfect water no longer exists, because everything has been touched by time and life. To find it, you would have to travel back to a spring at the very beginning. That is the gas of the red dot, a spring from the dawn of everything. And this purity slams straight into the central mystery. A giant black hole, 50 million suns heavy, sitting in gas so clean that almost no stars have ever cooked it. In the normal story, black holes come from stars. Stars pollute their surroundings with heavy elements as they live and die. A place with a giant black hole should be dirty with the ashes of countless dead stars. This place is spotless. The black hole is enormous, yet the neighbourhood shows almost no sign of the stellar generations that were supposed to build it. The ashes are missing. The furnace is huge, but there is barely any smoke. That single contradiction, a massive black hole in nearly starless gas, points toward a conclusion so strange that that scientists spent months making sure they believed it. To follow that conclusion, we first have to understand what those missing heavy elements really tell us about the stars that were never there. Stars are the factories of the universe. And in the red dot, the factories barely ran. Every heavy element you have ever touched was built inside a star. Carbon in your body, oxygen in the air, iron in your blood, gold in a ring. None of it existed at the start. Stars forged all of it in their blazing cores, fusing light elements into heavier ones over millions of years. When those stars died, some gently, some in titanic explosions, they scattered their creations into space. The next generation of stars and planets formed from that enriched debris. This means heavy elements are a kind of clock. The more of them you find in a place, the more stars have lived and died there. A galaxy rich in oxygen and iron has a long history behind it. Generations of stars that were born, burned and blew apart, seeding the gas again and again. Heavy elements are the ash left in the fireplace, proof that many fires have burned. The red dot has almost no ash. Its gas is nearly pure hydrogen and helium, which means only a tiny number of stars, if any real number at all, have ever lived and died there. The fireplace is cold and clean. Barely any fires have burned, and that is deeply strange for a place holding a black hole the size of a small galaxy's worth of mass. Here is why it matters so much. The classic way to make a big black hole is to build it out of stars. Huge stars collapse into small black holes when they die. Those small black holes merge and feed and slowly grow. But that whole process is filthy. It requires generation after generation of massive stars living and dying, and every one of them would pump heavy elements into the surrounding gas. Make a black hole the normal way, and you cannot help but leave a mountain of ash behind. The red dot left almost none. So the normal way seems ruled out. You cannot build a 50 million sun black hole from the corpses of countless stars, and then look around to find the gas still pristine, as if no stars ever burned. The story does not fit the evidence. The ash that should be there is missing. Picture a blacksmith's forge that has clearly produced an enormous iron gate. Now walk inside and find no soot on the walls, no cinders on the floor, no scorch marks anywhere. You would be baffled. That much iron demands a roaring fire, and a roaring fire leaves its mark. A clean forge with a giant product makes no sense, unless the gate was never hammered out of raw metal, in the usual way at all. That is the puzzle in physical form. A giant black hole, a spotless forge. Either an impossible number of stars burned and somehow left no trace, which nobody believes, or this black hole did not come from stars in the first place. And that second option is the door scientists were terrified and thrilled to walk through. If the black hole did not grow from dead stars, then how on earth did it form? To even ask that question properly, we have to face the oldest riddle in this entire field, a chicken and egg problem that just got turned completely on its head. Which came first, the galaxy or the black hole? For decades, most scientists quietly assumed the answer was obvious. The galaxy came first. That was the sensible story. Gas gathers in the early universe, stars ignite, a galaxy takes shape, glowing with new suns. Deep in its crowded center, the bigger stars die and leave black holes. Those black holes sink to the middle, meet, merge, and feed on the dense gas around them. Over vast stretches of time, they grow into the supermassive giants we see today. The galaxy is the nest. The black hole is the egg that hatches inside it. That picture felt right for a good reason. Everywhere we looked in the nearby universe, black holes and their galaxies seemed to grow together, hand in hand, matched in size as if raised by the same parent. Bigger galaxies held bigger black holes in a steady, reliable ratio. It looked like a partnership, a slow dance where neither partner ever raced too far ahead of the other. The red dot rips that dance apart. Here the black hole is not the egg quietly hatching inside a finished nest. The black hole is the dominant thing, heavier than its whole surroundings, sitting in gas so pure that the galaxy has barely begun to form. The nest is missing, or only starting to be woven, while the creature inside is already fully grown. So the old, comfortable answer breaks. The galaxy did not come first, something else did. This flips the chicken and egg riddle upside down. For years, the question felt almost philosophical, the kind of thing you argue about and never truly test. Now Webb has handed us a real object where the black hole clearly leads and the galaxy clearly lags. The egg is here. The chicken that supposedly laid it is nowhere to be found. Think of it like discovering a full-grown oak tree standing in a field with no roots spreading beneath it and no acorn anywhere in sight. Every instinct tells you the acorn and the roots come first, then the tree grows up slowly from them. Finding the mighty tree alone, with the ground around it still bare, would force you to imagine an entirely different way for trees to begin. That bare field is the red dot, and the oak is its black hole. The consequences are enormous, because this pattern reaches far beyond one lonely oddity. If black holes can lead instead of follow, then our whole understanding of how galaxies assemble may have the order reversed. Perhaps in the early universe, black holes formed first and then gathered galaxies around themselves, seeding them, pulling in gas, sparking the first stars. The black hole as parent, not child. That idea would rewrite textbooks. It would mean the giant black holes at the centres of galaxies today, including the sleeping one in the Milky Way, might trace their origins to something that existed before the galaxies did. The heart came before the body. But a wild idea like that needs a mechanism. If galaxies did not build these black holes out of dying stars, then some other process had to make them, and make them big, and make them fast. To find that process, we have to start where the normal story starts, with the humblest black holes of all, the ones born from a single dying star, and discover exactly why they could never grow big enough in time. Every giant has to start somewhere, and the usual starting point for a black hole is the death of a single star. When a truly massive star runs out of fuel, it can no longer hold itself up. Gravity wins. The core collapses in on itself in an instant, crushing down into a black hole, while the outer layers blast away in a brilliant explosion. The black hole left behind is small, as black holes go, weighing perhaps 10 to 100 times the mass of our Sun. Astronomers call this a stellar black hole, and it is the seed from which giants are supposed to grow. The word seed is the key. A seed is tiny. To become a supermassive black hole of millions or billions of suns, that little stellar seed has to grow by an incredible amount, multiplying its mass again and again until it is a monster. It does that by eating. Gas falls in, the black hole gets heavier, its pull grows stronger, it eats more. In a galaxy thick with gas, a seed can feast for a very long time. Given enough billions of years, this works. Our own galaxy's black hole likely grew this slow, patient way, sipping gas and merging with others across almost the whole age of the universe to reach its 4 million suns. Slow and steady, the seed becomes a giant. Nobody argues with that story in the modern universe. There's been plenty of time. The red dot ruins the timeline. Its black hole reached 50 million suns when the universe was only 700 million years old. That is a sliver of cosmic history. The first few weeks if you squeeze all of time into a single year. A stellar seed starting from a few dozen suns would have to grow at a ferocious, almost unbelievable pace to reach 50 million so fast. And that pace runs straight into a wall built by physics itself. Here is the trouble. Growing a black hole from a tiny seed to a giant takes time, and the early universe did not have much time to give. Between the birth of the first stars and the moment we see this black hole, there is only a narrow window. Cram all that growth into that window, and the numbers strain past the breaking point. Even feeding as fast as the rules normally allow, a stellar seed struggles to reach even a fraction of what we see. Picture planting an acorn and coming back a month later to find a towering ancient oak, its trunk wider than a car, its branches reaching over the rooftops. You would know instantly that something was wrong. Oaks take centuries. No acorn grows that fast. Either the tree is not really an oak, or it did not start as an acorn at all. The red dot's black hole is that impossible month-old oak. So astronomers were left with 2 escape routes, and only 2. Either these early black holes fed far faster than the rules should permit, breaking a cosmic speed limit that physicists thought was ironclad, or they never started as tiny stellar seeds in the first place, and were born already large, skipping the slow climb entirely. Both escape routes are radical. Both would change physics, and to understand why the first one is so hard, we have to meet the cosmic speed limit itself, an invisible brake that keeps every black hole in the universe from eating too fast. Its name is the Eddington limit, and the red dot may have shattered it. There is a speed limit on how fast a black hole can eat, and for once the black hole is its own traffic cop. It sounds backward. A black hole is the greediest object in existence, a bottomless pit of gravity that swallows anything that comes too close, even light. You would think it could gorge as fast as gas could fall in, but nature built in a break, an invisible limit that slows the feast, and understanding it is the key to why the red dot is so shocking. Here is how the break works. As gas spirals toward a black hole, it does not fall in quietly. It piles up, crashes together, and heats to blistering temperatures, glowing fiercely, blazing brighter than whole galaxies. That intense radiation pushes outward. Light itself has a gentle shove to it, and when the light is fierce enough, that shove becomes powerful, strong enough to hold back the very gas trying to fall in. So the black hole traps itself in a standoff. The more it eats, the brighter it glows. The brighter it glows, the harder its own light pushes gas away, choking off the meal. Feed too fast, and the black hole basically slams its own door with the force of its own brilliance. This balance point, where the inward pull of gravity and the outward push of light cancel out, is the cosmic speed limit. Astronomers named it after the scientist who first worked it out, Arthur Eddington. Think of trying to shovel coal into a furnace that is already roaring white hot. The heat blasting out of the open door is so intense you can barely get close enough to add more. The fire fights your feeding. The hotter it burns, the harder it becomes to feed it faster. That searing pushback is the Eddington limit made real. The furnace regulates its own appetite. This speed limit is why growing a giant black hole normally takes so long. A seed can only pack on weight so quickly before its own glow starts shoving the next meal away. It has to eat, pause as the radiation clears, eat again, in a slow rhythm across immense stretches of time. Patient, gradual, careful. That patience is exactly what the modern universe allowed, with its billions of years to spare. The early universe allowed no such patience. The red dot reached 50 million suns almost immediately after the first stars could have formed. If its black hole started as a tiny stellar seed and obeyed the speed limit the whole way, the clock simply does not work. There are not enough hours in the young universe's short day to grow that big while politely respecting the break. Which leaves two disturbing possibilities, and this chapter's cliffhanger lives inside them. Maybe this black hole ignored the speed limit entirely, feeding far faster than the break should allow. A reckless eater breaking a law physicists thought unbreakable. Or maybe it never needed to break the limit because it started out already enormous, born with a head start no seed could ever have. Both answers are wild. To weigh them fairly, we have to do the cruel arithmetic ourselves and actually count whether a well-behaved seed could ever reach 50 million suns in the time the universe allowed. When you run those numbers, the shortfall is nothing short of catastrophic. Let us do the impossible arithmetic, the calculation that broke the old story. Start with a stellar seed, a black hole left behind by a dying star. Give it a generous head start, say 100 times the mass of the sun. Now let it eat. Obeying the cosmic speed limit from the last chapter, feeding as fast as its own glare will politely allow. Ask a simple question. How long does it take to reach 50 million suns? The answer is brutal. Growing that much from 100 suns to 50 million means multiplying the mass hundreds of thousands of times over. Under the speed limit, a black hole can roughly double its weight only after a stretch of tens of millions of years. Double, then double again, then again, each doubling eating up another long chunk of time. To go from 100 to 50 million takes many doublings stacked one after another. Line up all those doublings, and the clock they demand runs longer than the entire age of the universe at the moment we see this object. The red dot's black hole existed when the cosmos was only 700 million years old. A patient stellar seed would still be nowhere near 50 million suns by then. It would need to have started growing before the first stars even existed, which is impossible, since it needs a dead star to be born in the first place. The timeline eats itself. The seed cannot appear until the first stars die. The first stars did not die until the universe was already a fair bit older. That leaves an even narrower window for all those slow doublings to happen. Squeeze all that growth into that narrow window, and the math snaps clean in half. Picture a runner who must cross 1,000 miles but can only ever run half the remaining distance each day, resting between each push. First 500 miles, then 250, then 125, slower and slower. Now demand that they finish the whole 1,000 miles before lunch. It cannot be done. The rules of their pace forbid it. The red dot seed faces the same trap. Its careful, halving, resting growth simply cannot cover the distance in the time given. This is the wall that stopped astronomers cold. Every honest calculation, done and redone by different teams, reached the same dead end. A normal seed, feeding at the normal limit, cannot become this black hole in this time. The shortfall is not a rounding error you could wave away. It is a gulf, a chasm between what physics allows and what Webb plainly shows. And that gulf is thrilling, because a wall this solid means one of our assumptions has to break. Either the speed limit is wrong for the early universe, and black holes back then could gorge far faster than the break should allow. Or the seed was wrong, and these black holes never started small, but arrived already massive, tens of thousands of suns from the very start. Scientists split into camps, each chasing one escape from the wall. The first camp bet on reckless feeding, on black holes that broke the speed limit and ate like nothing physics predicted. If they are right, then somewhere in the young cosmos, gas poured into these monsters at a rate that should have torn the whole system apart. And astronomers went looking for exactly that violent supercharged feeding. The first escape from the wall is simple to say and hard to swallow. What if these black holes just ignored the speed limit? Physicists have long known the cosmic break is not perfectly absolute. Under special, extreme conditions, gas can pour into a black hole faster than the neat balance point allows. The infalling matter can funnel down in thick streams, or find escape routes for the radiation to leak away, so the black hole keeps gulping even as it blazes. Astronomers call this supercharged feeding, eating beyond the limit. For a short, furious burst, a black hole might grow far faster than the patient rules predict. If early black holes fed this way, in wild, greedy bursts, the timeline could bend enough to make them fit. A seed, eating at several times the normal rate, would reach giant size much sooner. It would be a reckless eater, gorging so fast that its own furious glow could not keep up with shoving the food away. The break would be there, but the black hole would blow right through it. This idea is attractive because the early universe was the perfect place for a feast. Gas was everywhere, dense and abundant, freshly gathered and not yet blown apart by generations of exploding stars. A young black hole sitting in that thick soup would have an endless buffet pressing in from every side. With that much fuel crammed so close, perhaps some black holes simply could not help but overeat, breaking the limit by sheer force of supply. Picture a fire hose aimed into a small drain. Normally water trickles down at a steady pace, the drain letting through only so much. But blast enough water in with enough pressure, and it forces its way down far faster than the drain was ever meant to handle, overwhelming the usual limit through raw abundance. The early universe may have hosed gas into these black holes exactly that violently. For a while, this reckless eating idea looked like a tidy fix. It let black holes stay ordinary stellar seeds, born from dying stars, while still growing monstrous in a hurry. No exotic new physics needed, just a period of savage overeating in a gas-rich young cosmos. Many scientists found that comforting. It bent the rules without breaking the whole framework. But the red dot fights this fix, and the weapon it uses is the pristine gas we met earlier. Reckless feeding on that scale should be violent and messy. It should light up the surroundings, drive powerful winds, and involve generations of the massive stars whose deaths make the seeds in the first place. All of that should leave a chemical mess behind, a neighbourhood dirtied with heavy elements from stellar death. The red dot's gas is nearly spotless, almost pure hydrogen and helium barely touched. That cleanliness is hard to square with a history of countless dying stars birthing seeds and enriching the gas. The forge is too clean for a story built on so many stellar corpses. The reckless eater idea can force the timeline to fit, yet it struggles to explain why the ash is missing. So the second camp took a bolder swing. Forget growing fast from a tiny seed. What if the seed was never tiny at all? What if, instead of a black hole born from a single dying star, the early universe could birth a black hole already tens of thousands of suns heavy in a single dramatic act, with no messy stellar generations required? That idea has a name that sounds like science fiction: the heavy seed. What if the seed was never small? What if some black holes were born already huge? This is the second great escape from the wall, and it is bolder than reckless feeding. Instead of starting with a stellar seed of a few dozen suns and racing to grow, imagine a black hole that skips the tiny stage entirely. It begins its life weighing tens of thousands of suns, maybe even 100,000, all at once in a single event. Astronomers call this a heavy seed, and it changes the whole math of the race. Think about what a head start like that does. In the last chapters, we watched a small seed struggle, doubling slowly under the speed limit, unable to cross the distance in time. Now hand that seed a colossal advantage, starting the race already most of the way to the finish. A black hole that begins at 100,000 suns needs far fewer doublings to reach 50 million. Suddenly the timeline breathes, there is room, the clock works. The heavy seed wins the race through its birth by starting enormous while feeding at a perfectly ordinary pace. It respects the cosmic speed limit the whole way, feeding politely yet still arrives at giant size in the young universe. It never needs to break any laws of physics, it simply refuses to start small. The trick is all in the birth. Picture two climbers racing to the top of a mountain by noon. One starts at the very bottom and must scramble up the entire face, doomed to run out of time. The other is dropped by helicopter 3/4 of the way up, and only has to cover the final stretch. Same climbing speed, same rules, wildly different outcomes. The heavy seed is the climber who begins near the summit. It was placed high from the start. This idea also fits the strange clues we have gathered. It helps explain the black hole that outweighs its own galaxy, because a heavy seed is enormous before any real galaxy exists around it. It helps explain the pristine gas, because a heavy seed does not require generations of dying stars to build it. Born big in one act, it leaves no mountain of stellar ash behind. The clean forge suddenly makes sense. But a heavy seed raises a harder question than it answers. How on earth do you make a black hole tens of thousands of suns heavy in a single event? Small black holes come from single dying stars, and we understand that well. There is no such thing as a star 100,000 times the sun's mass that could collapse into a heavy seed directly. Ordinary stars top out far below that. So where does a heavy seed come from? Scientists have a candidate, and it is spectacular. Instead of a star collapsing, imagine an entire vast cloud of gas collapsing, all at once straight into a black hole, without ever bothering to become stars at all. A whole reservoir of primordial hydrogen and helium, falling inward together and vanishing into a single dark point. No slow burning suns, no supernova, just a giant cloud that skips being a galaxy and becomes a black hole in one plunge. That process has a name that captures its raw drama: direct collapse. It may be the strangest way to make a black hole in the entire cosmos, and the red dot might be the clearest evidence that nature actually does it. Imagine a cloud of gas so large it could have become a galaxy, choosing instead to become a black hole in one catastrophic plunge. This is direct collapse, the leading idea for how a heavy seed is born. In the normal story, a giant cloud of gas fragments. It breaks into countless clumps, and each clump ignites into a star. That is how galaxies fill with suns. But under the right rare conditions, a cloud can refuse to fragment. Instead of breaking into stars, the whole thing collapses together, pouring inward as a single mass until its own gravity crushes the center into a black hole tens of thousands of suns heavy. The key is stopping the stars from forming. For a cloud to collapse whole, it must avoid breaking into pieces, and clouds break into pieces when they cool down. Cool gas clumps easily. Warm gas resists clumping and prefers to fall inward as one. So direct collapse needs a way to keep a giant gas cloud warm and smooth, refusing to shatter into stars, right up until the moment it swallows itself into darkness. The early universe offered exactly those rare conditions in certain special spots. Recall that the primordial gas was almost pure hydrogen and helium with none of the heavy elements that help gas cool and clump. Pristine gas resists fragmenting. Add a nearby flood of intense light from a neighbouring young galaxy, bathing the cloud and keeping it from cooling, and you have the perfect recipe. A vast, warm, pristine cloud that cannot make stars, only a black hole. Picture a still lake on a freezing night. Normally the surface breaks into thousands of separate ice crystals, scattering into a rough sheet. But keep the water warm and undisturbed in just the right way, and instead of shattering into crystals, the whole body could plunge together in one motion. Direct collapse is a gas cloud that skips the scattering of stars and falls as one into a single dark drain. This idea fits the red dot with eerie precision. It explains the giant black hole in nearly pure gas, because direct collapse happens precisely where the gas is pristine and starless. It explains why the black hole outweighs its surroundings, because the black hole is born first from the cloud itself, before any real galaxy of stars can assemble. It explains the missing ashes, because no crowd of dying stars was ever needed. The black hole is the firstborn, and the galaxy comes later, if at all. One of the young scientists on the team said it plainly. This looks like a black hole without a substantial host galaxy, one that came before the usual stellar processes even began. That is a stunning sentence to say out loud. It means we may be staring at a black hole that predates the stars around it, a heavy seed caught in the act, formed by the direct collapse that theory long predicted but no one had confirmed. For years, direct collapse lived only in equations and computer models, a beautiful maybe. The red dot may be the first solid footprint of it in the real sky, a black hole that truly was born big. Yet there is a version of this idea even wilder than a collapsing cloud, one that reaches back further than the first stars, further than the first galaxies, all the way to the opening moments of the universe itself. There is an idea so bold it reaches past the first stars, past the first galaxies, all the way to the opening instant of time. What if this black hole did not form from a collapsing cloud at all? What if it was born in the first second after the Big Bang, before there were any stars, any galaxies, any structure of any kind? Physicists call such an object a primordial black hole, and it would be the oldest kind of object it is possible to have. Older than starlight. Nearly as old as time. Here is the thinking behind it. In the very first moments of the universe, everything was crammed together at unthinkable density, a searing sea of matter and energy churning violently. That sea was not perfectly smooth. It rippled, with some regions slightly denser than others. Where a patch of the young cosmos was dense enough, its own gravity could have crushed it on the spot right then, in the first instant, collapsing directly into a black hole without any star or cloud involved at all. If that happened, the universe would have been sprinkled with black holes from its very first second, seeds scattered into the dark before anything else existed. Some could have been tiny, others could have been large, ready-made giants waiting in the newborn cosmos. A primordial black hole would need no dying star, no collapsing cloud, no galaxy. It would simply have been there from the start, a piece of the beginning frozen into permanence. This possibility turns the red dot into something almost mythic. If its black hole is primordial, then it is older than its galaxy, older even than the very first star that ever shone. It would be a relic of the birth of everything. A shadow cast in the opening heartbeat of the universe still feeding 13 billion years later. The child that came before all other children. Picture the universe's first second as a pot of water flashing into a violent boil. In that chaos, most of the water churns evenly, but here and there a spot collapses inward with such force that it punches a permanent hole into the fabric of the pot. That hole never heals. It stays, long after the water calms, a scar from the very first instant. A primordial black hole is that scar, carried through all of cosmic history. The team studying the red dot said openly that its strange qualities point toward either direct collapse or something even more primordial, a heavy seed formed in that first second. They cannot yet say for certain which. Both ideas share the same radical core. This black hole was born big, without stars, at the very dawn or before the dawn of the shining universe. That is a breathtaking claim, and scientists do not make it lightly. Yet the evidence keeps pushing them toward it. A giant black hole in pristine gas, outweighing its home in the infant cosmos. Every clue whispers that it began before the normal rules of star and galaxy ever started to apply. And if primordial black holes truly exist, scattered through the universe from its first second, they would do more than explain one strange red dot. They might solve one of the deepest mysteries in all of science, a mystery about the invisible stuff that holds every galaxy together and that no one has ever been able to see. If black holes were born in the first second, they might be hiding in plain sight all around us, holding the universe together. To see why, we need to meet one of the biggest unsolved mysteries in science. When astronomers weigh galaxies, something does not add up. Galaxies spin so fast that they should fly apart, flinging their outer stars into the void. The visible matter, all the stars and gas we can see, does not have nearly enough gravity to hold them together, yet they hold. Something invisible is gripping them, something with mass, something we cannot see. Scientists call this unseen glue dark matter. It appears to outweigh all the visible matter in the universe several times over. It shapes how galaxies form, how they cluster, how the whole cosmos is knit together. And after decades of searching, no one knows what it is made of. It gives off no light. It refuses to shine. It only reveals itself through its gravity, tugging on the things we can see. Here is where the red dot's black hole gets thrilling. If the universe really did make primordial black holes in its first second, and made a great many of them, then those black holes could be part of the dark matter itself. Invisible, massive, scattered everywhere, gripping galaxies with their gravity while giving off no light. Dark matter might be, at least in part, a swarm of ancient black holes born at the beginning of time. This idea has floated through physics for years, always tantalizing, never proven. The problem was evidence. How do you find black holes that were born before stars when they emit no light of their own? They are the ultimate hidden objects, dark by nature, ancient beyond reach. For a long time, primordial black holes stayed a beautiful guess with no way to test it. The red dot may be a crack of light through that locked door. A black hole this big, this early in gas this pristine, is exactly the kind of object a primordial origin could produce. It does not prove that dark matter is made of black holes, but it shows that the young universe was capable of making giant black holes in ways we never confirmed before, which keeps the primordial idea alive and breathing. Picture searching a dark house for an intruder you can never see, knowing they exist only because doors keep swinging and floorboards keep creaking under invisible weight. For years you have only the creaks. Then one night, a single faint shadow crosses a doorway, the first hint of a real shape. The red dot is that shadow, a first glimpse that the invisible things gripping our galaxies might be exactly this kind of ancient darkness. If that turns out to be true, the consequences are staggering. The same objects breaking our theories of black hole growth could also be the missing mass holding the entire universe together. One mystery would answer another. The monster in the red dot and the invisible glue of the cosmos would be the same ancient thing, seen at last. That is an enormous idea to hang on a single object. So the natural question becomes, is the red dot truly alone? Or has Webb found others like it, a whole family of impossible early giants that together make the case far too strong to ignore? As it turns out, the red dot has a sibling, and that sibling sits even deeper in time. The red dot is not the only impossible black hole Webb has found. It has a sibling, and that one sits even closer to the beginning. A little earlier, another team went hunting through the deep sky and locked onto a distant object with a black hole at its heart. This one glowed when the universe was only 470 million years old, even younger than the moment we see the red dot. That makes it, for a time, the oldest black hole anyone had ever measured, a monster feeding in the deep dawn of the cosmos. Like the red dot, this sister object carried a black hole far too heavy for its youth. Estimates put it near 40 million suns, though the truly staggering part was the comparison to its home. Scientists calculated that its black hole might weigh anywhere from 1/10 to the entire mass of all the stars in its galaxy combined. The same sickness as the red dot. A black hole that dwarfs, or nearly dwarfs, everything around it. This mattered enormously, because it meant the red dot was not a lonely freak. Two separate objects, found by different teams using different methods, both showing the same impossible pattern. giant black holes, born too early, weighing too much compared to their galaxies. One strange object might be a fluke. Two, sitting at the very dawn of time, start to look like a rule. Different teams, different tools, the same disease showing up twice at the edge of time. That kind of agreement is exactly what turns a startling one-off into something a whole field has to take seriously. There is a beautiful human story tucked inside this discovery. Years before Webb ever launched, a scientist named Priyamvada Natarajan had worked out on paper what a heavy-seed black hole should look like in the early universe. She predicted their strange traits, their oversized masses, before anyone could see them. When Webb and its partner telescope finally caught the sister monster, its features matched her predictions with striking accuracy. She had described the creature before anyone laid eyes on it. Picture a naturalist who sketches a bizarre animal she believes must live in an unexplored jungle, based only on the shape of the ecosystem around it. Long, curved claws, a particular hunting style. For years, colleagues call it a fascinating guess. Then an expedition returns with a photograph, and there it is, claws and all, exactly as drawn. That is what happened here. The theory came first, and the sky confirmed it. That match sent a jolt through the field. When a bold prediction comes true so precisely, scientists start to trust the idea behind it. The heavy seed, born big through direct collapse, moved from a fringe possibility toward a serious explanation. Two monsters, both matching the theory, both breaking the old rules, both whispering that black holes can come first. But the sister monster was found using a different tool than the red dot, and that difference matters. The red dot gave up its secrets to Webb's careful reading of swirling gas. The sister monster revealed itself another way, through a kind of light our eyes can never see, captured by a second great telescope working hand in hand with Webb. That light is the telltale scream of a black hole caught in the middle of a meal. The sister monster gave itself away with a scream of light our eyes can never see. When a black hole feeds, the gas spiraling into it does not go quietly. It piles up in a searing disk, crushed and heated to temperatures beyond imagining, far hotter than the surface of any star. Matter that hot stops glowing in ordinary colours and starts blasting out X-rays, a fierce, high-energy light invisible to human eyes but unmistakable to the right telescope. X-rays are the signature of violence, the fingerprint of gas being torn apart at the edge of a black hole. To catch that scream, astronomers turned to a telescope built for exactly this, an X-ray observatory named Chandra, orbiting high above the Earth. While Webb read the object in infrared, gathering its gentle heat glow, Chandra listened for the harsh, X-ray shriek of a feeding black hole in the same spot. Two telescopes, two kinds of light, aimed at the same ancient smudge, each catching what the other could not. Chandra found the scream. Right where Webb saw the faint early galaxy, Chandra detected X-rays pouring out, the unmistakable mark of a black hole in the act of devouring gas. That double detection was the proof. The infrared glow showed the object existed at the dawn of time. The X-rays showed a black hole was actively feeding inside it. Together they nailed down both the age and the monster, and the X-rays told even more. The strength and character of that high-energy light let scientists estimate how much the black hole weighed, confirming it as a giant sitting where no giant should yet exist. The scream doubled as a measuring stick, letting astronomers weigh the beast from the sheer fury and character of its meal. The louder the scream, the heavier the monster hiding behind it. Picture standing outside a locked warehouse in total darkness, unable to see inside. Then you hear it. The deep, grinding roar of an enormous machine running full tilt behind the walls. You cannot see the machine, yet from the sheer volume and pitch of the roar, you know it is huge and you know it is working hard. Chandra heard the roar of the feeding black hole through the walls of 13 billion years. This teamwork between telescopes is how modern astronomy cracks its hardest cases. No single instrument sees everything. Webb drinks the ancient infrared glow. Chandra catches the violent X-ray scream. Only by combining them could scientists prove that a giant black hole was feeding at the very dawn of the cosmos, matching the bold predictions made years before. With the sister monster confirmed by its scream, the red dot confirmed by its swirling gas, and a theory that predicted both, the case grew heavy indeed. These were no longer isolated oddities to be explained away. They were becoming a pattern and a pattern demands a new story of how the universe works. Because if 2 impossible black holes turned up almost the moment astronomers went looking, then how many more are out there, hiding in the deep sky, waiting to be found? The answer, it turns out, is a great many, and they have been staring back at us from Webb's images all along, disguised as tiny, harmless red freckles scattered across the dawn. 2 impossible black holes could be bad luck, but Webb kept finding more. Once astronomers knew what to look for, the deep images started giving up more and more of these overweight monsters. Object after object showed the same disease. Black holes too heavy for their age, sitting in galaxies too small to have built them. What began as one shocking red dot, then a sister monster, grew into a crowd of misfits, each one breaking the same old rule in the same strange way. The pattern was consistent and damning. In the nearby universe, black holes are a tiny fraction of their galaxies, roughly 1 part in 1,000, the Plite ratio we saw in the Milky Way. But these early objects broke that ratio again and again, their black holes ballooning to enormous fractions of their host galaxy's mass. Again and again, wherever astronomers pointed at the young cosmos, the same impossible pattern surfaced. This is what turned a curiosity into a crisis for the textbooks. A single freak can be dismissed, explained away as a measurement error or a rare accident. A whole population cannot. When dozens of objects all sing the same impossible tune, the tune is real, and the theory that forbids it is the thing that has to change. The universe was telling astronomers loudly that their story of black hole growth had a hole in it. The scientist whose predictions matched the sister monster felt the ground shift under the entire field. She described the thrill of watching testable predictions made early in a career actually get tested and validated within her own lifetime. It is rare for a scientist to guess at a hidden truth and then live to see the sky prove it. Here, the sky proved it many times over. Picture a detective who finds a single strange footprint at a crime scene and wonders if it means anything. Then another turns up across town, and another, all matching, all impossible to explain with the usual suspects. At some point, the footprints stop being a curiosity and become a case that rewrites who the criminal must be. The early universe left footprints like that, all over Webb's images. Each new overweight black hole made the reckless eating explanation harder to defend, and the born big explanation stronger. If only one object had been too heavy, maybe it just fed unusually fast. But a whole population of giants, all in pristine early gas, all dwarfing their galaxies, points instead to a common origin. They were born big, through direct collapse or something even more primordial. The pattern demanded it. And this pattern reached beyond the giant black holes themselves. It connected to another Webb mystery we touched on earlier, the strange red freckles scattered by the hundreds across the young sky. Those little red dots had baffled astronomers from the start. Now, with the red dot's black hole weighed and understood, scientists began to suspect that the freckles and the monsters were the same phenomenon wearing different masks. If that suspicion holds, then Webb has not found a handful of impossible black holes. It has found an entire hidden population, blooming across the dawn of the universe and then vanishing, each one a compact monster in disguise. To understand that population, we have to look closely at the freckles themselves, the hundreds of tiny red dots that may each hide a giant. Scattered across Webb's deepest images are hundreds of tiny red freckles, and each one may hide a monster. From the very first surveys of the early universe, these little red points kept appearing, far more of them than anyone expected. They cluster in a particular era of cosmic history, the first billion years or so, when the universe was young and building its first structures. Then, as time moves forward, they fade and vanish, as if a whole population of objects bloomed at the dawn and then disappeared. Astronomers had never seen anything quite like them. At first, no one knew what they were. Too red, too small, too numerous. Some scientists guessed they were compact galaxies stuffed impossibly full of stars. Others suspected black holes hiding inside cloaks of gas. The debate raged, because the answer would reveal something huge about how the early universe assembled itself. Hundreds of mystery objects, all singing the same strange note, all waiting to be decoded. The red dot we have been following is one of these freckles, the clearest and best study of them all. That is precisely why the team chose it. Magnified 3 times over by Pandora's cluster, It was the rare member of the population bright enough to weigh directly. Crack this one, and you hold a key to all the others. Solve the clearest freckle, and the whole hidden population starts to make sense. And what the red dot revealed points a bright arrow at the rest. A giant black hole dominating a tiny, pristine, nearly starless object. If the red dot is that, then many of its fellow freckles are likely the same, each a compact monster in disguise, each a supermassive black hole hiding inside a small glowing shroud of gas at the dawn of time. The universe was not sprinkled with odd little galaxies, it was sprinkled with baby giants. Picture walking through a forest at night and seeing hundreds of faint, identical glimmers scattered through the dark. At first you think they are dewdrops catching the moonlight, harmless and pretty. Then you catch one up close and realise it is an eye, and that every glimmer in the forest is an eye, and you are surrounded by a whole population of creatures you never knew were there. That is the shift happening in astronomy right now. The dewdrops are eyes, the freckles are monsters, and the forest is far more crowded than anyone ever dared to guess. The sheer number matters enormously. A few impossible black holes might be freaks, hundreds of them, forming a whole class of objects across the early universe, cannot be waved away. They represent a genuine phase of cosmic history, a moment when the young universe was busy making compact giants in a way it does not seem to anymore. Something about those first billion years was special, and these freckles are the fingerprints of it. So the question sharpens. What exactly is a little red dot physically up close? A black hole, yes, but wrapped in what? Why so red? Why so small? Why do they bloom and then vanish? The red dot gave us the weight of the monster inside. The next step is to picture the monster in its shroud, a black hole wearing a cocoon so strange that scientists coined a brand new name for it. Picture a black hole wrapped so thickly in glowing gas that from a distance it looks like a single enormous star. This is the newest and strangest idea for what the little red dots really are, and scientists gave it a name that sounds like a contradiction. A black hole star. It is a supermassive black hole buried at the heart of a dense, swollen cocoon of gas, so thoroughly wrapped that the light escaping from it mimics the glow of a colossal star, larger than our entire solar system. The monster hides inside a shining shell of its own making. Here is the picture taking shape. The black hole feeds, and its feeding heats the gas around it until that gas blazes. But instead of that light escaping cleanly, it gets trapped and scattered inside a thick surrounding cloud of hydrogen and helium. The cloud glows from within, lit by the buried monster, puffing up into a vast luminous ball. From across the universe you see the ball, red and compact, and you might never guess a black hole hides at its centre. This idea neatly explains the freckles' two biggest puzzles. It explains why they look like tiny points rather than sprawling galaxies, because the glowing cocoon is compact, all wrapped tight around the central black hole. And it explains the deep red colour, because light struggling out through a thick shroud of gas emerges reddened and softened, its character changed by the journey through the cloud. The disguise is the cocoon. Scientists have found telltale signs of exactly this structure in some of these objects. The light carries fingerprints of dense gas surrounding a hidden source of radiation, the kind of pattern you would expect from a black hole enshrouded in a thick, swaddling cloud. One studied object showed all the pieces of the puzzle sitting together in the same place. A feeding black hole cocooned in gas, glowing like an impossible star. The black hole star stopped being a guess and started becoming a discovery. Picture a lantern wrapped in layer after layer of red silk. From across a dark field you cannot see the flame. You see only a soft, glowing red bundle, round and mysterious, giving no hint of the fierce fire buried at its centre. Unwrap the silk, and the truth blazes out. The little red dots are lanterns wrapped in silk, and the flame inside each one is a supermassive black hole. This reframes everything. The freckles are not strange little galaxies at all. They are monsters in swaddling clothes, black holes so young and so hungry that they have not yet blown away the gas cocoons they were born inside. The red glow is the nursery, and the thing growing in the nursery is a giant. It is a snapshot of a supermassive black hole in its infancy, still wrapped in the cloud that made it. But nurseries do not last. A black hole star is a phase. a fleeting stage in a much longer life. And that raises a haunting question about the hundreds of red dots that vanish as cosmic time marches on. If they were everywhere in the first billion years and then disappeared, where did they all go? What did these swaddled monsters grow up to become? The little red dots bloom across the early universe, and then, as time moves forward, they disappear. Where did they all go? This is one of the eeriest facts about them. They crowd the first billion years of cosmic history, hundreds upon hundreds of them, and then they thin out and vanish. Look at later eras of the universe, and the freckles are gone. A whole population everywhere at the dawn, absent by the time the cosmos matures. Objects do not simply cease to exist, so they must have changed into something else, shedding their disguise and becoming a new kind of thing. The leading answer is that they grew up. A black hole star is a phase, a swaddled infant stage. As the black hole keeps feeding, and the surrounding cocoon of gas gets blown away or used up, the object stops looking like a compact red freckle. The disguise falls away, the glowing shroud disperses, and what remains is a more familiar kind of object, a black hole sitting in a growing galaxy, no longer hidden, no longer red, no longer a mysterious dot. Think of it as metamorphosis. The red dots are the cocoons, and the cocoons do not last forever. Inside each one, a monster is maturing. When the gas clears, the creature emerges transformed, and it no longer resembles the freckle it once was. So the vanishing is really a graduation. The dots disappear because they become the ordinary giants that fill the later universe. If that is right, the implications are enormous. It means these swaddled monsters of the dawn are the ancestors of the great black holes we see everywhere today. The compact red freckles of the early universe grew up into the supermassive black holes, sitting at the centers of grown galaxies, including, perhaps, the sleeping giant in the heart of the Milky Way. The dawn's disguised infants became the elders of the cosmos. Picture a pond in early spring, thick with tadpoles, hundreds of them wriggling everywhere. Return to that same pond in summer and the tadpoles are gone. But look at the banks and you find frogs sitting in the reeds, grown from those very tadpoles. The tadpoles simply transformed into a new stage of life. The red dots are the universe's tadpoles, and the grown black holes are its frogs. This picture ties the whole story together in a single sweeping arc. Heavy seeds form at the dawn, born big through direct collapse or from the first instant of time. They wrap themselves in glowing cocoons of pristine gas, appearing as little red dots. Then they feed, shed their shrouds, gather galaxies around themselves, and mature into the supermassive giants that anchor galaxies across all of later cosmic history. If this arc is correct, then nearly every giant black hole in the universe today may trace its origins back to one of these strange early freckles, and further back still to a heavy seed born at the dawn. The monsters we see everywhere now would all share a single radical beginning. The whole family tree of supermassive black holes would have its roots in objects that came before galaxies. That idea reaches out and touches something very close to home, because it means the black hole at the center of our own galaxy might have started the same impossible way. And if these giants really did come first everywhere, then a famous law that scientists trusted for decades, a law linking every black hole to its galaxy, may be quietly falling apart. If the red dots grow into the giants we see today, then almost every great black hole in the universe may share the same impossible birth. For a long time, astronomers had no clear origin story for the supermassive black holes anchoring galaxies. They knew the giants were there, weighing millions or billions of suns, sitting at galactic centers everywhere they looked. But where those giants came from, how they got their start in the young universe, stayed frustratingly unclear. The seeds were hidden in the deep past beyond the reach of any telescope, until Webb. Now a possible answer is coming into focus, and it is sweeping. The heavy seeds born at the dawn, wrapped as little red dots, feeding and maturing across cosmic time, may be the source of nearly all the supermassive black holes that exist. Every giant at the center of every large galaxy could trace its lineage back to one of these strange early objects. The freckles of the dawn would be the ancestors of every monster in the modern sky. This would fill in the greatest missing chapter in the story of black holes. We understand how they feed. We understand how they warp space and bend light. What we never understood was how they got started, how the first ones formed and grew so fast. The red dots and their heavy seeds offer that missing beginning, a plausible root for the entire family tree, planted before galaxies even existed. The scale of this is worth pausing on. There are giant black holes in essentially every large galaxy. Count the large galaxies in the observable universe, and you are counting an almost unfathomable number of these monsters. If they all began as heavy seeds wrapped in glowing cocoons at the dawn of time, then that single, strange, early process shaped a feature of nearly every galaxy in existence. One origin story written across the whole cosmos. Picture discovering that every great river on Earth, no matter how wide or wild, can be traced back upstream to the same kind of hidden mountain spring. You had always known the rivers, seen them carve continents, but never understood where they truly began. Then you find the springs, high and cold and ancient, feeding all of them. Suddenly every river shares a common source. The heavy seeds may be the springs from which every supermassive black hole flows. This idea also reaches down to us in a personal way. The Milky Way's sleeping giant, our own 4 million sun black hole, would then have begun as one of these dawn-born seeds. The dark heart of our galaxy might be a grown-up little red dot, a monster that started before our galaxy existed and has been sitting at its center ever since, gathering the Milky Way around it across billions of years. That is a stunning inversion of the story we started with. We began by assuming galaxies build black holes. We may be ending with black holes building galaxies, seeding them, anchoring them, coming first. The parent and child have traded places across the whole universe, and if that trade is real, it shatters a rule astronomers relied on for decades, a beautifully tight relationship between the mass of a black hole and the galaxy around it. That rule held perfectly in the nearby universe. The red dot breaks it by a factor of thousands, and understanding why exposes just how deeply this discovery cuts. For decades, astronomers trusted a law so tidy it felt like magic. The red dot just broke it by thousands. Studying galaxies in the nearby universe, scientists noticed something remarkable. The mass of a galaxy's central black hole tracked closely with the properties of the galaxy around it. Bigger galaxies held proportionally bigger black holes, in a steady, predictable ratio, the roughly 1 part in 1,000 relationship we met in the Milky Way. Measure the galaxy, and you could guess the black hole. Measure the black hole, and you could guess the galaxy. They marched in lockstep. This tight relationship became one of the most trusted patterns in all of astronomy. It suggested that black holes and galaxies grow up together, hand in hand, regulating each other across cosmic time. The black hole feeds and blasts out energy that shapes the galaxy. The galaxy funnels gas that feeds the black hole. Neither races ahead. They co-evolve, locked in a slow, balanced dance, always keeping that steady ratio between them. The red dot stomps on that dance. Its black hole makes up 2/3 of the whole object's mass, thousands of times more than the tidy ratio allows. If the trusted law held here, the black hole should be a tiny sliver of its galaxy. Instead, it is the overwhelming majority. The lockstep is shattered. The black hole has sprinted so far ahead of its galaxy that the two sit on entirely different scales. This is a violation by an enormous factor, a gulf between what the law predicts and what Webb measured, far too wide to smooth over. And the red dot is not alone in breaking it. The whole population of early giants seems to defy the relationship, their black holes wildly overgrown compared to their galaxies. The tidy law that worked so well nearby simply falls apart at the dawn of time. Picture a rule that says a country's capital city always holds about 1% of the nation's people, a rule that holds true for every modern country you check. Then you discover an ancient land where the capital holds 2/3 of everyone, dwarfing the countryside completely. The rule you trusted was never a law of nature. It was a description of a particular era, and in an earlier age things worked entirely differently. The black hole law is the same. It describes today, not the dawn. This tells us something profound. The lockstep between black holes and galaxies was not there from the beginning. It developed over time. In the early universe, black holes could run far ahead, born big before their galaxies formed. Only later, as galaxies caught up and the two settled into their long partnership, did the tidy ratio emerge. The famous law is the end state of a relationship that started wildly unbalanced. So the broken law is actually a clue, pointing back to a time when black holes led and galaxies followed. It confirms the radical picture we have been building. Black holes first, galaxies after. The order reversed from what everyone assumed. And the reason astronomers can say all this with confidence comes down to one thing that set the red dot apart from every early black hole before it. For the first time, they did not have to guess. They measured the monster directly, and that single act of honest weighing changed how much we can trust everything else we thought we knew about the early universe. Before the red dot, every measurement of these early black holes rested on a guess. This time, scientists weighed the monster for real. Here is the quiet problem that had haunted the whole field. To weigh a distant black hole, astronomers usually rely on assumptions borrowed from black holes in the nearby universe. They see how bright an object is, or how fast certain gas moves, and they plug those numbers into relationships worked out from black holes close to home. It works reasonably well nearby. But applying those local rules to objects at the dawn of time was always a leap of faith. Nobody knew if the early universe played by the same rules. That uncertainty cast a shadow over every dramatic headline. Each time Webb reported a giant early black hole, a nagging doubt followed. What if the assumptions were wrong? What if these black holes only looked enormous because scientists were misapplying local rules to a universe that behaved differently? Maybe the monsters were smaller than they seemed, and the whole crisis was a mirage born of bad guesses. The doubt was real, and it was serious. The red dot erased that doubt. Because of the clean, orderly motion of its gas, the three-lensed copies checking each other, and the sheer clarity of this particular object, scientists could weigh its black hole directly, using nothing but the simple law of gravity and the measured speed of orbiting gas. No borrowed assumptions, no leap of faith, just speed, distance, and gravity. The same honest method that weighs the sun from the orbits of the planets. This was the first time anyone had directly weighed a black hole this deep in the young universe. A genuine, assumption-free measurement of a monster at the dawn of time. The lead scientist called it exactly that, the first direct measurement of a black hole's mass within the first billion years after the beginning. A milestone the field had been reaching toward for years, finally grasped. For the first time, a mass this ancient stood on solid ground, resting on measured motion rather than on borrowed hope. Picture a whole community of surveyors who had always estimated the heights of distant mountains using clever tricks and rules of thumb, never able to actually climb one and measure it directly. Their estimates might be right, but doubt always lingered. Then, for the first time, one team hauls their instruments to a single distant peak and measures its true height, foot by foot. Suddenly they have a real anchor, a known quantity to check all their estimates against. That is what the red dot became, a known anchor in a sea of estimates. A single object weighed honestly, directly, beyond argument, standing at the dawn of time as proof that the monsters are truly as massive as they seem. The crisis in black hole science was real, not a mirage. The giants are genuinely there, genuinely too big, genuinely breaking the rules, and this honest weighing did something generous for all the other measurements that came before it. Because when scientists compared their direct result to what the old borrowed assumptions would have predicted for this object, they found the two agreed. The guesses, it turned out, had been pretty good, and that agreement quietly rescued a mountain of earlier work, giving astronomers new confidence in the whole strange picture Webb had been painting. One honest measurement did more than weigh a single black hole. It quietly validated 1,000 others. Remember the doubt from the last chapter. For years, every early black hole mass came from borrowed assumptions, rules lifted from the nearby universe and applied on faith to objects at the dawn of time. Astronomers built an entire picture of the early cosmos on those assumptions, a picture full of impossible giants. But the whole structure rested on a foundation nobody had ever truly tested. If the assumptions were wrong, the picture could collapse. The red dot put the foundation to the test. Here, at last, was an object weighed two ways at once. Scientists could measure its black hole directly, using the clean motion of its gas and the simple law of gravity, and they could also calculate what the old borrowed assumptions would have predicted for the same object. Two roads to the same number. The question was whether the roads would meet. They met, The direct honest measurement and the old assumption-based estimate landed in close agreement. The borrowed rules, it turned out, had been giving trustworthy answers all along, even out here at the dawn of time where nobody was sure they would hold. The foundation was solid. The leap of faith had, against the odds, been landing on firm ground. The doubt that had shadowed the field for years finally began to lift. This was an enormous relief for the entire field. It meant that the mountain of earlier measurements, all those headlines about impossible early giants, had not been built on sand. The assumptions worked. The masses were reliable. The crisis was real, confirmed now by a direct check rather than resting on hope. One clean measurement reached backward and steadied everything that came before it. Picture a bank that had been recording thousands of deposits using a scale everyone worried might be miscalibrated. For years, doubt hung over every entry in the ledger. Then someone finally weighed a known, certified bar of gold on that very scale, and it read exactly right. In a single moment, every past weighing gained new trust. The scale was good, the ledger was good, the red dot was that certified bar of gold, and it proved the scale. The lead scientist said as much, calling the agreement a phenomenal result. A sign that the masses of other early black holes had not been overestimated after all. The giants were genuinely giant. The population of overweight monsters was genuinely overweight. Webb's strange early universe, full of black holes that came too soon and grew too big, was confirmed as real, not an artifact of shaky math. And that confirmation matters enormously for everything we have explored. The broken law, the heavy seeds, the hidden population of red dots, the whole radical picture of black holes coming before galaxies, all of it rests more securely now, anchored by one object weighed honestly. The story holds together. The universe really did make giants at the dawn. Which brings us back to the strangest implication of all, the one hiding inside the red dot from the very beginning. If the black hole came first, then the galaxy is only now starting to form around it. We are watching, in real cosmic time, something almost no one imagined possible. A black hole building a galaxy from the inside out, growing its own home around itself. We were taught that galaxies grow black holes. The red dot shows the opposite. A black hole growing a galaxy. Step back and look at what we have assembled. A giant black hole, born big at the dawn, sitting in a tiny, pristine object with almost no stars. 2/3 of everything there is the black hole itself. The gas is nearly untouched, close to the original recipe of creation. This is a black hole with a galaxy barely beginning to gather around it. The center exists first, and the surroundings come later. We are catching the process at the very start. Scientists describe the red dot as possibly being in the earlier stages of building a galaxy around itself. The black hole came first. Now its gravity pulls in the surrounding pristine gas, gathering material, and in time that gas will cool and clump and ignite into stars. Generation by generation, a galaxy will assemble in the black hole's grip, growing outward from the monster at its heart. The heart came first, and the body grows around it. This flips the whole picture of galaxy formation on its head. In the old story, gas gathers, stars form, a galaxy assembles, and only then does a black hole grow deep inside it, a late addition to a finished structure. In this new story, the black hole is the founding stone, the seed crystal, the anchor around which everything else accumulates. It does not join a galaxy. It starts one. If that is what we are witnessing, then the red dot is a galaxy being born in reverse. The center exists before the surroundings. The monster exists before its meal. Over the hundreds of millions of years after the snapshot we see, this tiny pristine object could pull in more and more gas, spark waves of star formation, and slowly transform into a full galaxy, with the once lonely black hole finally sitting at its heart, the way our giant sits at the heart of the Milky Way. Picture a pearl forming in an oyster. It begins with a single tiny grain at the center, and then, layer by layer, the pearl builds outward around that seed, wrapping it in shell after shell, until a whole gem exists where once there was only a speck. The black hole is the grain. The galaxy is the pearl growing around it, one layer of stars at a time. Without the seed at the center, the pearl would never form. This idea gives the black hole a role no one expected. The black hole becomes the founder, the origin point, the very thing the galaxy grows from, rather than a passenger riding along inside it. Across the early universe, These heavy seeds may have been scattering through the dark, each one becoming the anchor of a future galaxy, seeding the cosmos with the centers around which everything else would eventually assemble. It is a humbling thought. The galaxies that fill the universe, that hold the stars and worlds and perhaps the life within them, may all have grown outward from ancient dark seeds that came first, including our own. The Milky Way, with all its billions of stars and its single pale blue world where you are listening right now, may have begun as one of these monsters, growing its vast body around a dark and ancient heart. But what would it actually be like to stand near such an object, at the dawn of time, before the galaxy formed? The reality is stranger and more hostile than almost anywhere in the universe today. Imagine standing near the red dot at the dawn of time. It would be one of the most hostile places the universe has ever made. Forget the calm, star-filled night sky, you know. This object is a compact ball of gas, only a small town wide by cosmic standards, glowing fiercely from the fury of a feeding black hole at its center. The whole region blazes, lit from within by matter screaming as it falls into the dark. There is no gentle scattering of distant stars here. There is a searing, enveloping glow, the light of a monster's endless meal filling the entire sky around you. The gas itself would be alien, almost pure hydrogen, helium, the raw ingredients of creation, with almost none of the heavier elements that make up the familiar world. No oxygen to breathe, no rock, no metal, no carbon for anything living. Just the two lightest gases, hot and glowing, pressed close in a cramped, brilliant space. It is a place from before the universe learned to make the stuff of planets and life. And at the center of it all, invisible yet dominating everything, sits the black hole. 50 million times the mass of the sun, a bottomless well of gravity swallowing gas in a ceaseless torrent. Around it, the infalling matter would form a blazing, roaring disk, crushed and heated beyond imagining, shrieking out radiation across every wavelength, including the fierce X-rays we met earlier. To be near it would mean being bathed in a storm of energy no living thing could survive for an instant. The gravity would warp the space around you, bending the very paths of light. Look toward the center, and the sky itself would appear distorted, twisted by the immense mass, the glow smeared and curved around the invisible monster. Time itself would stretch near that gravity, running slower the closer you drew to the black hole's edge. It is a place where the ordinary rules of space and time visibly bend. Picture standing inside a furnace the size of a solar system, filled with roaring luminous gas, at the center of which lies a drain heavier than a small galaxy, pulling everything toward a point of no return, warping the light and slowing the very passage of time. That is the neighborhood of the red dot at the dawn, beautiful in a photograph across 13 billion years, utterly lethal up close. Yet for all its violence, this hostile ball is a place of creation. The pristine gas glowing around the monster is the raw material from which stars and galaxies will one day form. The fury we imagine is the fury of a beginning, the chaotic, blazing nursery in which a future galaxy is taking its first step, hellish and generative at once, a cradle that looks like an inferno. Standing there, if you somehow could, you would be witnessing the deep origins of cosmic structure, the moment before galaxies, when black holes ruled and light and gas swirled in raw abundance. You would be seeing the universe in its violent infancy, building the seeds of everything that came after, including, eventually, the calm and star-strewn sky we live under now. And that leads to the deepest question this whole discovery raises, a question that reaches from the dawn of time all the way to the pale world where you stand. If black holes came first, and built galaxies around themselves, then what does that make them? Passengers, or architects of everything, including us? If black holes came first and galaxies grew around them, then the monsters may be the architects of the entire cosmos, including us, sit with the full weight of that. For most of the history of astronomy, black holes were seen as endpoints, the dead remains of collapsed stars, the graveyards at the centers of galaxies. Terrifying, yes, but ultimately passengers, riding along inside structures that formed without them. The galaxy was the creator. The black hole was a dark accident buried in its heart. The red dot suggests the reverse. If these heavy seeds formed at the dawn, before galaxies, and then gathered gas and sparked stars around themselves, then black holes were not the endpoints of cosmic history. They were the starting points, the founding stones, the dark anchors around which the luminous universe assembled itself. Every galaxy, every cluster of stars, every glowing spiral may have grown from a monster that came first. This reaches all the way to us. Our own galaxy holds its sleeping giant, 4 million suns of darkness at its centre. If the new picture holds, that black hole may have been one of the dawn's heavy seeds, forming before the Milky Way, then gathering our galaxy around itself across billions of years. The sun, the earth, the oceans, and every living thing would then trace their cosmic address back to a black hole that came before it all. That means the black hole at our galaxy's heart is not a distant, unrelated horror lurking far away. It may be the reason our galaxy exists in the first place, the seed that gathered the gas that formed the stars that forged the elements, that built our world and our bodies. The monster and the maker would be the same thing. The darkness at the centre would be the origin of the light. Picture a great cathedral, admired for its soaring stone and brilliant windows. For centuries, visitors assume the walls came first, and the foundation stone was laid somewhere along the way. Then someone digs beneath the altar and finds a single ancient cornerstone, older than everything above it, the stone on which the entire cathedral was raised. Remove it, and nothing would stand. The black hole may be that cornerstone buried at the centre of every galactic cathedral in existence. There is a strange beauty in this. The objects we fear most, the swallowers of light, the points of no return, may be the very things that made the universe habitable, that gathered the material for stars and planets and life. Creation and destruction bound together in one dark heart. The monster is the maker. The end is also the beginning. We cannot say for certain yet. The evidence points this way, strongly, but the story is still being written, and the universe has fooled confident scientists before. What we can say is that a single red dot, weighed honestly across 13 billion years, has forced humanity to consider that black holes may be the architects of everything we are, and this is only the first clear glimpse. The red dot cracked the door open. Behind it waits a whole population of these ancient giants, dozens already spotted waiting to be studied, each one a chance to confirm or overturn this staggering new picture. The race to rewrite the story of the cosmos has already begun. One red dot broke the old story of the universe. Now astronomers are hunting for the rest, and the search has only begun. The team behind the red dot said it plainly. Objects like this cannot have been rare in the early universe. They are already sifting through more of these strange ancient smudges, hunting for others that show the same impossible pattern, black holes that outweigh their galaxies, monsters that came before the stars. Each new one is a test. Each new one could confirm the radical picture, or complicate it, or crack it open in a way no one expects. This is how science surges forward. A single clear case, weighed honestly, forces the field to take an idea seriously. Then the hunt begins for more, because one object can be argued about, but a whole population cannot be ignored. Webb has handed astronomers a rich new territory to explore. Hundreds of red dots, dozens of candidate giants, a whole era of cosmic history suddenly open for study. The dawn of the universe has become a frontier. And the questions waiting there are the deepest ones we can ask. How exactly are these black holes born? By direct collapse or from the first instant of time? How many are there? Do they really grow into the giants at the centres of galaxies today? Did black holes truly come first and build galaxies around themselves? Is our own galaxy the grown child of one of these ancient seeds? Every one of these questions is now testable, thanks to a telescope that can finally see the dawn. The tools are only getting sharper. Webb keeps staring deeper, gathering more of these objects, weighing more of these monsters. Other great telescopes join the hunt, catching the X-ray screams of feeding black holes, mapping the swirling gas, checking the masses. The predictions made years ago on paper are being tested against the real sky, one ancient giant at a time, theory and observation closing in together on the truth. Picture the first explorers cresting a ridge and seeing, spread below them, an entire unmapped continent, vast and strange and full of things no one has ever named. They cannot chart it all in a day, but they know, standing there, that everything downstream will be different now. The map of the world has changed. The red dot is that ridge, and the early universe is the continent, and astronomy has only just begun to walk into it. What makes this moment so thrilling is that we are alive for it. For the whole history of our species, the dawn of the universe was invisible, sealed away behind distance and time beyond any hope of seeing. Now a golden telescope 1,000,000 miles from Earth has torn that seal open, and the first thing it showed us was a monster that should not exist. A black hole older than its galaxy, breaking the rules we thought were unbreakable. We began with a simple assumption. Galaxies come first and build their black holes slowly, over billions of patient years. We may be ending with the opposite truth. Black holes came first, born big at the dawn, gathering galaxies around themselves, seeding the cosmos, including the one we call home. The story of the universe is being rewritten right now in real time by a single red speck of ancient light. And the most astonishing chapters are still waiting, out there in the dark for the next time we look.